So this is Math 341, Stat 341, Lecture 4. I had mentioned that every now and then I want to have a day where we just spend it doing problems. And this is the advantage of having lectures recorded. This is not necessarily the day it was chosen, but given that I found out very late last night or this morning that I was going to be taking my son to the doctor, I wasn't sure if I was going to be able to get back in time for this lecture. So I've already said just watch the video for the material. It's again more of the standard material. And then what I want to do for class today is either some of the homework problems that were assigned, or if there are other problems in the book that you think are interesting and you want to do, or if they're just some general probability problems you want to ask me. I want to try to have a couple of these problem sessions in the class where it's not lecture, it's not new material coming in, it's let's play Stump the Professor. And let's give the professor a problem on the board and watch the thought process. So first, are there any problems from the homework that people would like to see?
I just want to make sure for problem 4, the one with set A and set B,
Right.
equal in cardinality.
Yes.
Could you go over
Sure.
that?
So we just want two sets, such A and B have the same cardinality. And they have to live in the plane. They can't be on the line. So one possibility is you could just have A be maybe the point 0, 1, 2, 3. And you could have B maybe 0, 0, 0, 1, 1, 1, 1, 0.
Is it all right if I gave like an equation for B? Like I said B was like A with like an element of A like A, and then the y coordinate would be A cubed?
Sure.
Okay.
There's lots of ways you can do it. So this is a discrete way where I have two sets of 4 elements. Another thing is I could have a straight line here, and I could have a parabola like this. And then I have a one-to-one mapping where every point on the line. As an aside, did you know that there are as many points from -1 to 1 as there are from -2 to 2? So that these two sets have the same number of elements. So -1 to 1, same size as -2 to 2. There's lots of different levels of infinity. And so, given that we have a little free time today, let's talk a little bit about infinity. This is the danger. So here's one simple proof. Send x to twice x. The sets are the same. They have the same cardinality. There's a one-to-one onto map between the two sets. If you give me an element in A, there's a unique element in B. You give me an element in B, there's a unique element in A. No two elements go to the same element. So in some sense, the sets have the same size. In another sense, they don't. What's the size of this?
4.
4. And what's the size of this?
2.
2. So in that sense, they have very different sizes. Here's another way to see things. Here's 0, -1, 1. And then what I'm going to do is draw a line here at 45 degrees. And so every point here so if I look like that, do you see -1, 1 being into one-to-one correspondence with this line? And then what I can do is I'll then draw 45 degree line from this, and have these points all coming down like this, and that'll give me the line from -2 to 2. Just do two 45 degree angles like that. Anybody heard of the Hilbert Hotel? Hilbert Hotel is wonderful. Every room is filled, but it can always take more guests. So you have a countable infinity. And so countable infinities are the only types of infinities we're going to really care about in this book. Now, yes, -2 to 2, this is an infinity. It's often called the cardinality of the continuum. But when we deal with sets, if we're going to be assigning probability to a set of disjoint, distinct objects, they've got to be countable. So you have rooms 1, 2, 3, etc. So every room is filled, and a guest comes. And the guest is extremely important. They're a Williams alum. You don't want a Williams alum standing. So, but you don't want to be mean to the people who already have a spot in your hotel. So if you've never seen this pub before, how can you accommodate this new person?
Can we not answer? We know the answer.
So you can answer, you know the answer. Yes.
You just like move every one of them over
Yeah.
500.
You tell person 1, hey, move to room 2. Tell person 2, hey, move to room 3. Tell person 3, move to room 4. And then that opens up room 1. Could you handle 2 people arriving? Yeah. Could you handle infinitely many people arriving? Yeah.
By giving them like the even rooms.
Yeah. So you would move 1 to 2, you would move 2 to 4, you would move 3 to 6. And if you do that, you'll free up all the odd rooms. So you could actually handle infinitely many more people showing up. It's a wonderful hotel. Other questions from the homework? Did people have fun with the division?
I thought that was really cool.
So what did people get when you divided?
Fibonacci.
Fibonacci's. What do you think? Amazing coincidence?
Probably the 998. 999 has to do with that.
How? This should at least be a surprising result, correct? Do you think it's always going to be the Fibonacci numbers? Yeah.
No, I think it's going to repeat eventually.
Well, that's sad. Why? Yes.
Wouldn't it stop once the number goes beyond the third digit?
Yeah, the problem is it seems to be padding some numbers, and they're not really talking to each other. So this is going to be a really good topic to discuss as to why this works. I'm going to prove it. Right? So, and the material we're doing here is actually material we're going to put in the bank for later in the semester. It's one of the greatest things in mathematics. Generating functions. Right. So, consider f0 is 0, f1 is 1, and fn plus 1 is fn plus fn minus 1. This is the Fibonacci numbers. Now, we have not talked about Fibonacci's yet in this class, correct? Okay. I have a lot of students at Williams who work with me on problems related to the Fibonacci numbers. There's actually a 12-person governing board of the Fibonacci numbers, internationally recognized. I am either the newest or the second newest member. I wasn't sure which one of us got the tap first at the conference. So I am one of the 12 people. So if you have an issue with Fibonacci numbers, let me know. There will be an international conference on Fibonacci numbers in the University of Sarajevo in July 2020. If anybody does research with me on Fibonacci numbers, you will actually have an opportunity to present at the conference. My favorite picture about the conferences is the 2018 conference was as good as the 2016 and the 2014 conference combined. And they have, of course, a cute cap going on in the background while this is being said. Once I give you this, everything about the Fibonacci numbers is now known. Everything follows from this relation. They're completely specified. The problem is, how do you extract the information? So one of my favorite formulas is there's actually an explicit formula for any Fibonacci number. It's 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. This is the golden mean. It's greater than 1 in absolute value. This is less than 1 in absolute value. So as n gets very, very large, this becomes negligible. The nth Fibonacci number is approximately the golden mean to the n divided by root 5. If you want to then estimate it, just find whatever the closest integer is to that, and you'll have your Fibonacci number. There are many ways you can prove this. You can prove this by induction. You can prove it by the method of divine inspiration. This is one of my favorite proof techniques. The way the method of divine inspiration works is you go, aha! And then you write down the answer, and then you check and see that it works. The problem is it's not always known when the divine inspiration will hit. You know, and if you have, I don't know, a timed exam, sometimes you may not be divinely inspired before it is time to hand in the exam. But if you have a guess, you can check and see, does it work? This is not an unreasonable thing. So one of the big themes in this course is my answer reasonable? So imagine I told you, screw learning probability. How about the following? If you write down by hand, no computer, no calculator allowed, the first 100 Fibonacci numbers, I'll give you an A+ for the class. Deal or no deal? Deal. What if I said 1,000? How big is the 1,000th Fibonacci number? How long would it take you to do that? Is this a deal you want to take?
What do you get if you don't do it?
You're no longer allowed to be in the MathStat major.
Oh.
We turn our back to you, and you have to go to Amherst.
Deal.
So would you do 1,000? Do you think you can do 1,000 before the semester's over?
Yeah.
And how much time would you spend on it? How many digits is it going to be? How many digits can you add? We will make the assumption that you never tire, don't need sleep, don't need food, don't need a social life. Hopefully these are assumptions. And that you will not make any algebra mistakes.
Oh, that would be.
So we'll assume you always add correctly. I might actually do the Fibonacci numbers base too. Although then the digits become longer, there might be a little bit easier arithmetic to do. How big is the 1,000th Fibonacci number? Well, it's the golden mean to the 1,000. So you can actually do this calculation later, estimate how big is the 1,000th Fibonacci number, figure out how much addition can you do a second. We would probably want to see how much addition can you do in a minute and divide that by 60. And then figure out, do you think you could actually do this before the semester ended? You should be able to make these ballpark estimates. For those of you who are going to have interviews with technical companies, this is precisely the type of problem they love to ask you. It's, how many people in the US do you think like the following, or this or that? You're making these reasonable estimates. Right? So we have this, we could prove this. There's a beautiful way to prove this through the generating functions. So g for generating, g of x is defined to be the sum and goes from 0 to infinity of fn x to the n. Now, at first glance, this seems foolish. I don't know what the Fibonacci numbers are, so I'm going to form an infinite sum, and then just pinning your homework over there. So I'm going to form an infinite sum where the coefficients of my powers of x are the Fibonacci's. And I'm going to use this to get information about the coefficients. This seems a little off. It's not terrible. The reason is we actually know everything about the Fibonacci's from the recurrence relation. We just have to extract that information. The whole idea of generating functions, and we will use this later in the semester when we prove the central limit theorem, is you create a global object. And by understanding the global object, you can often deduce information about the local objects. Now, what is your first thought when you see an infinite sum? What are you concerned about?
Does it converge?
Does it converge? So you have hopefully taken classes, Math 150, we've done some things with sequences and series, and we have all these convergence tests. I need to know how quickly the Fibonacci's grow. Well, I knew how the Fibonacci's were, I couldn't even. Right? Yeah. It feels like we're arguing in circles. But I know fn plus 1 is less than or equal to twice fn. So that implies that every time I increase n by 1, my Fibonacci number essentially doubles. Or, I'm sorry, at most doubles. Now, I've got to be a little careful because it goes 0, 1, 1. That's a real pain in the ass. But essentially, we get fn is less than or equal to 2 to the n. The only problem is the Fibonacci goes 0, 1, 1. Oh, wait, no. We're good. Oh, yeah, okay, excellent. No problem at all. Excellent. We can take those quotes away. So we know the Fibonacci numbers are growing at least as fast, growing no faster than 2 to the n. But we also know fn plus 1 is greater than or equal to twice fn minus 1. So every time we increase n by 2, we increase by at most a factor of 2. And that will get us a lower bound, f of n is greater than or equal to square root of 2 to the n. So we're doing these very quick calculations. The Fibonacci numbers are growing faster than root 2 to the n, but slower than 2 to the n. So if I take the absolute value of x less than 1/2, this is going to converge by the ratio test. I can actually do better if I actually know the true size of the Fibonacci numbers, but this series will converge as long as the absolute value of x is less than 1/2. All right, I'm now going to do the algebra in public. You are welcome to write this down. I have this written up in slides, and I can just send you the slides. You never, ever, ever want to do algebra in public. Unfortunately, as a professor, you often have no choice. So this will allow me to use something that was mentioned, I think, earlier in the book that you've already read so far, the bring it over method, to do some integrals, where you end up getting the unknown on both sides of the equation, and as long as the coefficient is not 1 on both sides, as long as it's not the same value on both sides, bring it over, and now you have maybe like 1 minus 1/4 of what you want equals something that's known. So if I know 3/4 of it, I multiply both sides by 4/3. Not a big deal. So g of x is going to be sum and goes from 1 to infinity of fn xn. Oh, no. Let me do it differently. It's just, what's the best way to do the algebra? Right, so let's look at the sum and goes from 0 to infinity of fn plus 1 x n plus 1. Okay? I can look at this. This is almost the same as g of x. My smallest term is f1 x to the 1. I'm missing the f0 x to the 0. Oh, but what is it? f0 x 0.
0.
0. So this is actually the same as g of x, since f0 x to the 0 is just 0. So this is just another way of writing g of x. This is the same as the sum and goes from 0 to infinity of fn plus fn minus 1 x to the n plus 1. And now it all comes down to, let's do algebra well. This is the same as the sum and goes from 0 to infinity fn x to the n plus 1 plus the sum and goes from 0 to infinity fn minus 1 x to the n plus 1. So let me be a little bit careful now. Let me start this at 1, not at 0. So if I start that at 1 and not 0, then this is not g of x, it's going to be g of x minus x. Because now I'm missing, my first term here is f2x squared. I'm missing the f1 x to the 1 term. I don't have to worry about the f0 x to the 0 term. When you look at this, we have fn x to the n plus 1. If you listen, it's screaming at you to do something. I got to step away, it's so loud. Much better. Now we don't have the grasping mode. What is it screaming at you to do?
Change the index.
Change the index. And so how would I do that? It's something that I do very nicely. I could do that.
No, you can factor out an x.
Factor out an x. G of x is defined as a sum of fn x to the n. I have fn x to the n plus 1. I've got one extra power of x. Let's pull out one power of x. And this is going to just be x times the sum, and goes from 1 to infinity of fn x to the n. And what do I want to do for the next one? I have fn minus 1 x to the n plus 1. How many powers of x do I want to pull out? 2. So I'll have plus x squared, the sum n goes from 1 to infinity of fn minus 1 x n minus 1. And so now we can see that we are very close to something good. And this will allow me to review. Oh, this was not on, so I'm not sure how much of the earlier stuff was recorded. Hopefully it was still getting the volume. Okay, so we now have g of x minus x from the left-hand side. The first term here is, well, when I sum from 1 to infinity, that's really the same as g of x. It's going to be x g of x, and the next term is x squared, and what do I have? I think I also have g of x. So I can bring all the g of x's to one side, so I get 1 minus x squared, g of x is equal to x. So g of x is x over 1 minus x squared. Now, if you want to prove Benet's formula, what you can do is you can use probably the most favorite integration technique from Calculus 2. Is the sarcasm sufficient? Okay, what's your most favorite technique? What do you pray to God you get to do on a homework problem or an exam in Calc 2? What's your favorite?
Integration by parts.
No, we actually like it. This is hysterical. We love integration by parts. What's the least favorite?
Quotient rule.
No. It may be so hated you may have mentally blocked it out. The worst technique from Calc 2, the one that people hate more than any other technique.
Is it like when you split the denominator?
Yes! You see that? The partial fractions. Yeah, I've seen people going like this. Okay? So, it may be the case that a lot of your previous professors and teachers were sadistic bastards. But that doesn't mean partial fractions is not useful. What you can do is you can write this as x times a over 1 minus alpha x plus b over 1 minus beta x. And you can factor the polynomial 1 minus x squared. So you have 1 minus x squared is 1 minus alpha x times 1 minus beta x. And then you can expand each one of these using the geometric series. And then that will give you g of x is x. And then when you expand these using the geometric series, you'll get a alpha to the n, x to the n, plus b beta to the n, x to the n. And that's how you get Benet's formula. That's one way to get Benet's formula. Okay, this is generating functions. The miracle is when we have a closed form expression like this. When you have a closed form expression, there is a tremendous amount of inference you can do. Okay. Now the question is, why is this related to the homework problems? There's got to be some connection. Either that or I apologize for the first 25 minutes of today's lecture. How is this related to the problem of 1 divided by, what was it, 998,999? Right. Do we all agree that this is what g of x is? So one of the things we saw, okay, so who said So what's the connection?
So you put in 1,000.
Yes. So we know that this is g of x, and we know this equals x over 1 minus x squared. So if we take g of 1 over 1,000, you're going to have a sum, and goes from 0 to infinity, of fn over 10 to the 3n. And that will be 1 over 1,000 over 1 minus 1 over 1,000 minus 1 over a million. And that's where the fraction comes from. By taking nice values like this, I can choose just how many digits and how long I want to go. So it's remarkable. We actually have closed form solutions for these weighted sums of Fibonacci numbers. I can't just sum all the Fibonacci numbers because that would go off to plus infinity. So I put in these weights. And that's where the 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 2, 0, 0, 3, 0, 0, 5, that's where it all comes from. And you can see that eventually it's going to break down. But 1 over 1,000, that's clearly less than a half, so the series will converge. I can put this in here. So when we prove the central limit theorem later, this is going to be one of the key techniques, is this idea of generating functions. We're going to do a lot with generating functions later in the course, so it's actually not bad to see them here. So there was a reason why I gave you those numbers. And then, of course, what you can do is you can say, well, are there other sequences that I can put in here and find a generating function that also has a closed form expression and then get something nice? Would there be something if I wanted to have, say, 001, 004, 009, 016, 025? Could you do something with perfect squares? Yes? Okay. All right. Any other questions on the homework before I just open it up to just questions in general? Does anybody have any question in general? Okay, then what I'm going to do is I will actually derive now the formula for the squares. 001, 004, 009, 016. Some of you may be thinking, oh my God, I have a mathematician teaching me. Okay, that is true. But what we are doing now is we're putting material in the bank that we're going to use later. What we're going to do is we're going to talk about one of the most useful ideas in probability. So we want to calculate quantities for distributions. Is there anybody here who has not heard of a mean or average value? Okay. Is there anybody here who has not heard of a standard deviation? What comes next? No, variance is really the same as the standard deviation. It's just a square. What's the third moment? What, yes? Skewness. What comes after skewness? Kurtosis. All right, what comes after kurtosis? Yeah, you just slap somebody in that. Oh, is it what?
I'm not sure. Is it heteroskedastis?
It could be. I lose it up for, but it could be. Email me if you are correct for. When I was a sophomore, I was a sophomore at Yale. I was visiting a friend of mine who went to Harvard. And I saw in the Science Center that they listed grades from the physics exam. And they didn't just give the mean and the standard deviation for the class. They also gave the skewness and the kurtosis. So the really anxious Harvard pre-med students could really see how they did relative to everyone else to such an incredible degree of precision.
Give the curve. Give the distribution.
Well, I mean, to some extent, you actually did have the distribution because they posted all the grades just with your identifying numbers, so it wasn't by names. So you could actually, but they also summarized by saying, here's the mean, standard deviation, skewness, and kurtosis. Yeah, I know, Mom, I know my grade isn't that good, but the kurtosis was. So differentiating identities. This is one of my favorite techniques in all of mathematics. It requires a little bit of analysis to make it rigorous. We're not going to worry about that. Have you ever seen like a home shopping video where they have some product and they say, and if you're one of the first so many callers, we'll throw in absolutely free, a pair of Ginsu knives or something like that? This is kind of how I feel like differentiating identities. Identities are the bread and butter of mathematics. If you get an identity, you are thrilled, you celebrate. We've already proven an identity in this class. We proved it on the first day of class. What formula did we prove on the first day? The basketball. So we proved the geometric formula. The sum, x to the n goes from 0 to infinity, is 1 over 1 minus x. So this is the geometric series. And everything is fine so long as the absolute value of x is less than 1. Wonderful formula. How would you feel if I told you I can get you infinitely many more formulas from this? Wouldn't that be wonderful if you had a procedure that generated new formulas from old? All you have to do is just be willing to play fast and loose with the mathematics. So I'm going to take d by dx of both sides. Is that being recorded, or maybe just? So I'm going to take the derivative with respect to x of both sides, and in fact, I'm going to multiply by x afterwards. Now, you have to be extremely careful in mathematics when you switch orders. The derivative of a sum is the sum of the derivatives. You've proven this in calculus. You proved it only for sums of two functions. For finite sum, you can do this. If I give you a plus b plus c, and I want to take the derivative, this is the method of grouping. This is the same as a plus b plus c, take the derivative. Then this is the same as a plus b derivative plus c derivative. This is the same as a prime plus b prime plus c prime. And then I can drop the parentheses. So this is the grouping proof. And so if you know the sum of two functions, that the derivative of that is the sum of the two derivatives, you can get 3, you can get 4, you can get 5, you can get any finite number. That does not mean you can do it infinitely. It does not mean the derivative of an infinite sum is the infinite sum of the derivatives. That has to be justified. And it's not always the case. We saw with Fubini's theorem that there are times when you can't switch the orders of integration. So you have to be careful. So what I want to do is switch the orders of a sum and a derivative. And so yeah, I'm going to just erase all of this. I'm going to say, yeah, but this class is co-listed. It's math and stat 341. So let's focus on more the stat part and not so much the math part. And let's just take the derivative through the infinite sum and not really worry about things. And then doing that, life is really good. X, d by dx of x to the n. And then the derivative on this side, when the dust settles, is x. I'll just say it's x d by dx of 1 minus x inverse. Well, the derivative of x to the n is just n x to the n minus 1 times x. We'll get n x to the n. And over here we'll get negative 1, 1 minus x to the negative 2. And then the derivative of this gives me another negative 1. So the negatives reinforce, and we get x over 1 minus x squared. So the sum of n times x to the n is x over 1 minus x squared. The difficulty is justifying the derivative of the infinite sum as the infinite sum of the derivatives. It can be justified. One of the reasons it can be justified is the geometric series is essentially the nicest possible infinite series I can give you. And the reason is, if you chop off the geometric series at one point, let's say you look at the first 1,000 terms, then everything that goes from that point onward is also a geometric series. And you can use this to make all of these arguments rigorous. If people want to, we can do that afterwards. Right now, let's just do it like this. We'll accept it, we'll move on. What would be a good value of x to take? Well, if we take 2, the series is going to explode. So if we took 1/2, it would converge. But we want to get something cute like we did for the Fibonacci numbers. Right? So what would be a good choice to take for x?
1 over 1,000.
Yeah, take 1 over 1,000. So if you take 1 over 1,000, then that's going to give us 1 over 1,000 divided by, now, 1 over 1,000, so we would have 999 squared over 1,000 squared. I think we would have, let's see, 1 over 1,000 then we would have 1 minus 1 over 1,000 would be 999 over 1,000 squared. 1 of the 1,000 should cancel. I think it should be 1,000 over 999 squared. So if we take 1,000 and divide by 999 squared, which somebody was kind enough to open up mathematics on my computer, it starts 0.001, 0.002. Mathematics only gave me 6 digits. So I'm going to do set accuracy. Let's do 50 digits. I don't really do it. So it gives me 001, 002, 003, 004, 005, 0059. What? Interesting.
Maybe it's not accurate.
Oh, I see what the problem is. I did 1,000.0 divided by 999. And so when I did 1,000.0 divided by 999, Mathematica did some approximations. And then when I said, do that accurately to 50 digits, it had already done some approximations. I have to remove the approximation first. And so now if I just do 1,000 divided by 999 squared, now it works. So this is the method of differentiating identities. We will use this to analyze a whole slew of probability distributions later in the semester. Freshman year, when you meet people, what are the standard questions you ask somebody? What entry are you in? Is that the first question you ask somebody?
Name.
Name, okay, so hopefully name first, okay. Name, then what entry? What else? What classes are you taking?
What sports do you play?
What sports you play? I thought I heard somebody say, where are you from? Right? There's a couple of standard questions that you always ask, right? Do you agree that you have a bunch of standard questions when you meet somebody? It's the same when you meet a probability distribution. Oh, hi, nice to meet you. What's your mean? What's your standard deviation? And then if you really want to get to it, what's your kurtosis? What's your skewness? Except instead of saying kurtosis and skewness, we talk about moments. And so again, we're putting some good material in the bank for later in the semester. And so we will often do things with integrals and continuous distributions because the calculations are nicer. So the nth moment is the integral from minus infinity to infinity of x to the n times your probability density dx. So the mean is the first moment. The standard deviation is related to the centered moments. And the idea is it's very similar to Taylor series. If you know all the Taylor coefficients, hopefully you know the function. It turns out that is not the case. There are some functions where bad stuff happens. But if things are nice, hopefully if you know the Taylor coefficients, you know something about the function. The same is true in probability. If you know the moments, hopefully you can figure out what the distribution is. And it turns out that this idea of differentiating identities is very valuable for calculating these moments. So we have now the sum, n goes from 0 to infinity, of n, x to the n, is x over 1 minus x squared. What could we do now? What could I do now? I've still got like 7 minutes to fill. Yeah.
You can do it again. So
Yes. So, has anybody ever read the instructions on shampoo? Just, I hope you're using it properly. So, lather, rinse, repeat. Technically, do you repeat once or do you keep repeating infinitely often and is all that you can do for the rest of your life, lather, rinse, repeat? I don't know. But I like the idea of the shampoo school of mathematics. Once you have something, do it again, do it again, do it again. Keep pushing it forward. See what you can pull from this. We did a lot by differentiating once. Well, what happened if we tried it again? Let's take again x d by dx. And so we'll have the sum, n goes from 0 to infinity. We'll now have n squared x to the n. And now we have x times the derivative of this. How do we take the derivative of that?
Is that coefficient or
So how do we do it?
It's not like a arc, like a tree metric function. Or
Well, I need to take the derivative
90 degrees,
of x over 1 minus x squared. How do I take the derivative of that?
Use the product rule or the quotient
You
rule.
use the product rule, the quotient rule, or you go to something like mathematical and whatnot, and you just put in the derivative, and either one is fine. All right, so what will we get? Well, I will just have mathematically do it. And mathematical also has a function called simplify. So I will multiply by x and simplify. And when the dust settles, we get, oh, mathematical, why would you do that? All right, so it's got negative x over 1 plus x. But it's got negative 1 plus x, so the negative signs pull out. All right, so it's 1 minus x cubed. So now, what would be a good value to put in for x? What would be a good value to take for x?
do it again.
Yeah, same value.
Yeah, take 1 over 1,000. And so we get 1, 0, 0, 1. 2, 3 zeros, 3 zeros. Divided by 997. 0, 0, 2. I think 999. And so if I now take that function, so if I take that and I look at 50 digits accuracy, I get 001, 004, 009, 016, 025, 036, 049, 064, exactly as you expect. If there is a nice function lurking in the background, you can actually generate very interesting fractions like this. I don't really know of any applications of generating interesting fractions like this, other than just, isn't it kind of cool that you can see this going on for a while, and then the pattern breaks down. But it will go on for a while. So in terms of just the cuteness, you know, I happen to like this, but again, that's a matter of personal taste. What really matters is we saw 2 great ideas today that I was not planning on getting to until later in the semester, but it's not bad to see things early and often. The first was this idea of a generating function. The idea of you have some local data and you combine and you get a global object. And somehow, amazingly, you can sometimes deduce things about the local data back from the global object, but you have this global object that you can now analyze. And from that global object, you can deduce a lot of things. The first thing we deduced was a triviality where this fraction looks like the Fibonacci numbers. That's not important. But what's important is that we can start to now find closed form expressions like this. These will come up when we try to study moments of a probability distribution. And these are the equivalent of asking, what's your name, what's your entry, where you're from, what are you majoring in, what sport do you play? These are the things you ask any probability distribution. And the answers guide you in terms of what the behavior is. And so over here, when we start differentiating identities, all of a sudden, we can still get closed form expressions. And we can then get values of things. And we will use this later to calculate the moments of various distributions. And some of these moment calculations will become trivial when we can use these differentiating identities. The challenge, of course, is justifying what we're doing. So given that we have a few moments left, I will quickly justify it for the geometric series. And then I will leave this as that if you really want to understand why this is going on, you should take real analysis. So when I teach multivariable calculus, and I almost surely should not see any of you in that class in the spring, but when I give that this is a prereq, The class I always want students to know is linear algebra, which is the next class. Here, the class I want you to know is real analysis. It's what we need to do this stuff rigorously. So let's let f of x be 1 plus x plus dot 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 x to the n plus x to the n plus 1 plus x to the n plus 2. So this is a geometric series. So this is the same as 1 plus x to the n plus x to the n plus 1, 1 plus x squared, and so on. So f of x is 1 plus x to the n plus x to the n plus 1, and in fact, you get f of x back. And the idea is when you're trying to do the analysis, this is now a finite sum. So if you wanted to try to say, well, what would happen if I took the derivatives? The hope is maybe you can show the derivative coming from this piece is going to be tending to 0 as it gets very, very large. Because as long as x is less than 1, when I raise x to the n plus 1 power, that's going to be trivial. In fact, if I take the derivative of this, if I use the product rule, I would get n plus 1 x to the n f of x plus x to the n plus 1 f prime of x. So if x is less than 1 and n is huge, these terms are going to be insignificant. So essentially, the derivative should just be the sum of the derivatives, which is the result you want. This is not a rigorous proof. This is hand waving, but just trying to give you a sense of how would you make this rigorous. And for the geometric series, we are fortunate that we actually can do something like that. All right. So today was dealing with Cameron and his medical issues. Monday we'll be dealing with Kayla and her medical issues. So there will be no physical class on Monday. Just you watch the video. Physical classes will resume on Wednesday.